Hello everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 3 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good introductory overview of enterprise storage. Let's kick off Module 3, Networking and Interconnects. Every piece of the infrastructure stack has to communicate somehow, but it's certainly not magic. Let's learn what goes into making each piece communicate. This module will be a little bit shorter than some of the others, as networking is usually one of those areas where we need to know the pieces of the puzzle, but we may not have nearly as much involvement with each of these layers as some of the other ones that we're going to be talking about. We're going to start with discussing networks and storage interconnect fabric, and then work our way through the stack through switches and consumption rates, talking about peak throughput, the endpoint interconnects with both HBAs and NICs, and then start monitoring utilization through the components. And then we're going to start talking about things that you can leverage from a SQL Server perspective, such as jumbo frames, VLANs, software-defined networking, and then dedicated networks. First of all, I truly hope that your server room does not look like this. This was a real photo that I took a few years back. My job was to uncover why their SQL Server failover cluster instance was unstable. It turns out that their heartbeat network cable for their physical FCI was right in the middle of this rat's nest of cabling. The end of one of the cables had a broken clip that secures it into the networking switch port and was held into that port because of gravity and friction from the other cables. Whenever someone would come and fiddle with the networking cabling, it would jiggle the cable just enough to where it would occasionally interrupt the communications on the cable and was triggering an FCI failover. When I first saw this, I wanted to get a chainsaw and go through all the cabling so that they would start over, but that's not really reasonable. What is networking? Networking and interconnects are the basic components that allow individual servers and applications to communicate with each other. Every single thing inside your data center that deals with transport of data of any kind has to go through this networking and interconnect topology. We're going to break down what's involved with each of these components and talk through things that you can do to make your SQL Server experience even better. There are a lot of components inside your data center that do have to communicate. Shared storage, just like we were talking about, has to communicate at very high rates to all of your servers. The servers themselves need to communicate with each other. Network and fabric interconnect switches facilitate this communication. Then you've got endpoints for the users in the applications, such as desktops and tablets and application servers. And then, if you're leveraging cloud components, we have to figure out how to get there and back. So we're going to start with the networking for regular server communication. These pieces start with Ethernet switches for our servers and our storage if our storage is network connected. Back in the day in data centers of the past, 1 gigabit was a standard for quite some time. 10 gigabit started to reduce its adoption price over time and has become the new standard in most modern data centers. If you look at the higher end data centers, or the components that let us connect multiple switches together, the speeds can increase up to 25, 40, or even 100 gigabit. I know they're even working on faster. Most of the time, for normal workloads, 10 gigabit is just fine. Usually at that point, our bottleneck to performance is more on code or underlying infrastructure components rather than the network. If we look at just storage traffic, sometimes companies elect to use what's called storage fabric for storage connectivity, which includes fiber optics for each endpoint. Usually, this is just storage only, or maybe to connect multiple switches together. Storage fabric speeds are measured in a little bit different increments of speed. Today, you'll see 4, 8, 16, or 32 gigabit speeds in the data center. They're always developing ever faster speeds, just like with regular networking. The communication signal has to originate somewhere. For storage fabric, a host bus adapter, or HBA, is the interconnect component that allows these fiber optics to transmit. For regular network adapters, we may have a connection for the network that we're used to, which is the RJ45 connector. It looks like a thick analog phone connection if you probably have these around your house. In modern data centers, we may need faster and more shielded cables, so the SFP Plus standard was created, which uses a much less error-prone shielded cable with a fancy transceiver on each end. Either way, it still acts like a regular network, so just make sure that when you buy new servers, you have the right connection for your network switches. Network Ethernet communication does have a little bit of overhead associated with it. The communication protocols involved can slow down the interconnect speed a little bit. You can see here the 3 main interconnect speeds that we see in modern data centers, 1, 10, and 40 gigabit. If you just look at the raw theoretical peak speed, we should be able to see 128 megabytes a second, 1.25 gigabytes a second, and 5 gigabytes a second respectively. But if you look at the actual overhead involved with these interconnects, the actual rated throughput is a little bit lower. Our actual peak throughput is about 115 megabytes a second, 940, and 3.8 gigabytes a second, give or take. Notice how the overhead at 1 gigabit is different for the faster speeds. For 10 and 40 gigabit Ethernet, in order to get the maximum possible speed out of that interconnect, we have to deal with enabling something called jumbo frames. Back when the Ethernet standard was created, they found that the equipment could not really handle a single payload greater than 1500 bytes. So they created a standard called the Maximum Transmission Unit, or MTU, that's standardized on a 1500 byte payload. It sends 1500 bytes in one payload and then asks for an acknowledgement of receipt. This was back in the day when network switches were measured in kilobits and had low megabit rates. However, modern network switches are much more capable and powerful than they used to be. The act of transferring and checking a 1500 byte payload is actually too much overhead to fully take advantage of a 10 gigabit network or faster. More recently, an option in modern switches was introduced to increase the MTU. The concept of a jumbo frame is a payload that is greater than 1500 bytes. The industry is standard on a 9000 MTU payload and calls them jumbo frames. On a 1 gigabit network, you're not going to see any real improvements, so don't worry about enabling this there. However, on a 10 gig or above network, if your network or storage demand is very significant, you should investigate enabling jumbo frames to get greater peak throughput potential. On average, I can see above a 20% peak performance gain or more on network throughput with jumbo frames enabled between your servers. This is where the challenge comes in with network administrators. Every single networking component between the two devices that you want to enable jumbo frames between must be configured to allow jumbo frames. This presents somewhat of a challenge for network administrators because they have to make sure that they get every device and port updated to allow this. If an endpoint is not configured, but the source is trying to send a jumbo frame, you end up with something called network frame fragmentation, where the jumbo frame gets rejected and the source has to retry with a bunch of payloads at a regular frame size. This constant retry mechanism can slow your network throughput by 10 times or more. There are ways to validate that these components are actually set up end-to-end properly, so it's more of a process issue than an actual technical one. VMware specifically has a utility built into the ESXi layer called vmkping, where you can send a large payload packet to another ESXi server and make sure that it gets there properly. If it does not, then you know at least one component in between those servers is not configured properly. I find jumbo frames very useful for both network-connected storage and if your SQL servers or other servers are moving around large amounts of data constantly. This can include if you write your SQL Server database backups to a network share. Validate and verify through your performance monitoring if you're actually able to send and write data that quickly, and if so, investigate using jumbo frames. We'll talk more about this once we hit the operating system level. Just so you know, SQL Server's default data payload is actually larger than the one regular-sized packet. The default networking packet size for SQL Server is 4 kilobytes. That means that you're sending 3 regular MTU packets for every bit of SQL Server communication. If you find that jumbo frames would help you, you enable jumbo frames inside your operating system, and then you can change your payload size inside SQL Server to 8 kilobytes. This will comfortably fit one payload inside one networking frame. Just make sure to do some testing, as I never like to overcomplicate this and make changes just for change's sake. If you find that this helps your SQL Server communication, explore what it's going to take to enable this end-to-end and take advantage of larger payload sizes. If you're looking at testing the maximum possible throughput between a couple of your servers, you can do this with a free utility called iPerf. iPerf is a simple Windows or Linux download that you can run on 2 servers. You set up one from a command line as a server and run the other as a client. It pushes the network and validates maximum end-to-end throughput rates. It does not measure response time, unfortunately, so you may need to resort to ping for that level of testing. We have a document on our other website here in case you want a printed guide for how to use this. But let's do a quick demo so I can show you how iPerf works. You can download iPerf for Windows pre-compiled and ready to go from the website iperf.fr. If you're running this on Linux, just do apt-get or yum or whatever your repository management is to download it from there. Usually, apt-get install iPerf. Nice and straightforward, completely compiled, free, ready to go. All you got to do, download it, extract it to the file system of each of the 2 machines you want to test between. I have 2 machines here, iPerf 1 and 2. We're going to run the second one as the receiver of the test. So you'll notice I have it staged here at C drive util folder, iPerf 3 executable. There's a Sigwin DLL that comes along with it, nice and harmless. Run this as an administrator in an elevated command prompt or PowerShell prompt. iperf3.exe space -s will launch this as a server. So you can see we are now listening on port 5201. It's automatically assigned. If you have firewalls between the machines, you may have to either poke a hole there or change the port that this is listening on. There's command line parameters to do all of that. We'll go ahead and jump to the other machine. I have the same copy of iperf staged on this machine. We're going to run this as a client against the other machine. So you can see iperf3-exe, -c for client, iperf2 to go to the destination machine, -t10 for 10 seconds, -p10. This is going to do 10 worker threads. I find that on a 10 gig network or above, there's just some quirks with the program where it just doesn't really want to max out the available network throughput. Whereas if you run more than one worker thread, it can fulfill and you really fill the pipe. So we're going to go ahead and run this. And you'll notice I've got 10 spawned. And for each one of these, it's going to give us average throughput ratings. Kind of pulses for about the 10 seconds, once a second. And you'll notice here we have a sum. In that 10 seconds, it transmitted 7.41 gigabytes at an average throughput of 6.37 gigabits per second. On a 10 gigabit network with absolutely nothing done to it. So no jumbo frames, no receive side scaling, no Windows auto tuning disabled, none of that stuff. This is about what you can expect. In future modules, we're going to talk through tuning all of these layers above this virtual machine and the networking throughput so that we can figure out not only what our peak potential throughput actually is, but be able to measure the tuning that we do and make sure that everything is actually making a difference, a positive gain. Because if we see a negative gain, undo what you just did. Okay, we'll talk through those here in future modules. Monitoring and managing network infrastructures may not be any of our focal points. However, guidance can be given to your networking team to ensure and validate that they are using the appropriate monitoring tools to measure your network switches. The individual port transfer rates themselves, when compared to the maximum throughput for each, needs to be monitored to make sure that you're not maxing out an individual switch port. The uplinks between the switches must also be monitored because if the uplink is a lot slower than your demand between the switches, that could be slowing you down very quietly, and it's very difficult to detect from inside your SQL servers. Another layer is inside the switch itself to monitor the port group controller CPU usage. If the switching rate is high enough, you could max out these CPUs, and that could be a bottleneck to performance. Some switches expose this usage and others do not. Every one of these components should be monitored and reviewed routinely to simply confirm that none of these components are acting as a primary bottleneck. Hopefully, you can even add some alerting that will help you determine when you're close to capacity. One layer that is commonly missed in my experience is specifically regarding blade servers. All the virtual machines running on the blades and the blades themselves are regularly monitored like normal. The network adapters that the blade sees are also monitored properly. However, if the network adapters that the blade uses are virtually presented from the blade enclosure, such as in the Cisco UCS blade platform, the network or fiber adapters that are present in the back of the blade enclosure itself may not be appropriately monitored. You could have seemingly underutilized blade-level network adapters present, but the adapters in the back of the blade enclosure could be maxed out and struggling. Make sure this layer is monitored appropriately and the metrics distributed across the teams just to make sure that that layer is not acting as a bottleneck. One last architectural item to note is that your network administrators can create a virtual networking segment called a VLAN. A VLAN is a logical segment on the network, usually reserved for a type of server or particular networking subnet. It's a great way to segment and isolate traffic so that your security visibility is lower. These VLANs must be defined in the physical networking switch layer as well as mapped in virtual networks created in the virtual machine layer. We'll talk about these in a later module. If you find that additional networking segmentation will help you, work with your networking administrator to create the appropriate VLANs. You can see in the diagram we have a SQL Server production network VLAN. Server communication traverses this just fine and the server can communicate with anything else that it needs. What if we want to have a DMZ that is publicly accessible? We can create a separate VLAN with much tighter security around it and place our servers into this network. It's almost the same as having a completely dedicated networking switch just for this networking segment. It comes in handy for a lot of different purposes, and you can extend these into the virtual machine layer to reduce complexity and cabling. That'll about do it for our physical networking review. Stay tuned because next is our physical server discussion in Module 4.